Okay, so thank you very much for the nice introduction, and thank you very much for the invitation. It's a real pleasure to be here, and I'm looking forward to a very exciting day. But first, you have to listen to me, of course. I'll do my best not to obliterate too many brains. So I just want to start by saying that this talk is not just my own talk. I prepared this together with Mary Sheeran, who is my colleague and my wife. Here she is. She's also a researcher in functional programming. And so there's no side effects in our household. So the talk is named after my paper that we just heard about. But although I wrote this more than 30 years ago, and it's become a very popular paper since then, it's probably my most read paper, then, of course, functional programming is much older than this paper. And also, a lot has happened in the last 30 years. So what I'm going to give you is a collection of highlights. I'm going to talk about some of the classic papers in the field. I will talk a bit about what's in this paper. And I'll talk also about some of the personal highlights that Mary and I have experienced during the course of our careers. So let's go right back to the beginning. Functional programming started round about 1940, but it was very different in those days. In 1940, functional programming was very, very minimal. So for example, if you want a minimal programming language, who needs Booleans? Right. What is a Boolean for? A Boolean is only there so you can make a choice. Well, we can make choices with functions. Let's define true and false to be functions that make choices. If they're going to make choices, they have to have two things to choose between, so let's give them two arguments. And now we can just define true, we'll say true, chooses the first one, false chooses the second. There we are. So do these functions really correspond to Booleans in any meaningful way? Well, yes, because now I can define if then else. Right? Here's if then else. It takes a bool, that's one of these functions, and the then branch and the else branch, and it just chooses then or else by calling the Boolean. So in a language with functions, we don't need Booleans. Cool. What about numbers? Who needs numbers, really? I mean, what's a number for, an integer, if not for counting loop iterations? So let's define 2, for example, to be a function that takes a loop body f and a starting value x, and just calls f twice. There we are. In the same way, 1 will call f once, 0 will call it 0 times. You get the idea. So now, for any positive integer, I can define a function that I say corresponds to it. But how can I convince you that these functions really do represent integers? Well, I should show you how to turn them back into a normal integer. So suppose you write these definitions in Haskell. How can I convert 2, for example, back into a normal Haskell integer? Well, I can just call it in the Haskell shell. This is the Haskell read-eval print loop. And I'll run a loop that increments 0. Okay, so +1 is Haskell notation for the increment function. So this says increment 0 twice. And what do we get? 2. There we are. So these really do represent integers because I can get the integers back out from them. Well, is this just a trick? What if I want to do arithmetic on these things? Can I do that? Look, we can add together these functions just by sequencing loops. How do you execute a loop body m plus n times? Simple. First you execute it m times, then you execute it n times. That's what this does. We're taking the loop body f. First I'm executing it n times, and then m times on the result. What about multiplication? How can you execute a loop body m times n times? You nest the loops. What could be simpler? There we are. So we have an inner loop here that calls f n times, and then an outer loop that does all of that m times, and that's just the product of m and n. Does this really work? Well, you can try it out in Haskell. You can just say, OK, let's add 1 to multiply 2 and 2, and then we'll take that function and we'll use it to iterate the increment function 5 times on 0, and yes, we get 5. So this is great. Now you can have a functional programming language without Booleans or numbers. And that means you can write the factorial function. I'm sure you've all been waiting for it. So here is factorial a la 1940. And so I'm just using my if then else. If n is 0, I'll return 1. Otherwise, I'll multiply n by factorial of n minus 1, as usual. And does this work? Well, I can just try it out. I can construct the function for factorial 5 and use that to run increment from 0. And yes, we get 120. It works. Now, there's a couple of things I haven't shown you how to do. There's the is0 function. That's easy. How do you tell if a function n represents 0? Well, you use it to iterate a loop body that returns false, starting from true. Okay, so if there's 0 iterations, you'll get true. If there's more than 0, you'll get false. Easy. And we also need to decrement a number. And the less said about that, the better. But you can do it. And in fact, you can carry this idea further, and you can take any data structures, lists, tuples, you name it, and represent them all by functions. So you don't need any of that stuff. And the man who realized this was Alonzo Church. They're called Church encodings after him. Why did he want to do this? Well, because Church was interested in using functional programming as a foundation for mathematics and a foundation for computation. He wanted to show that you could build everything else out of just functions. So he had a very theoretical interest. But actually, these ideas have had a practical impact as well. You may not know this, but early versions of the Glasgow Haskell compiler actually represented data structures this way. Not numbers, obviously. That would be stupid. But data structures. There was a man called Jon Fairbairn was the first to do this. He built his own functional language compiler, and he implemented lists and tuples. He did a quick hack, and he used the Church encodings. And then after a little while, when the compiler was working a bit better, he thought, OK, now I should implement them properly. So he implemented built-in data structures, and the code went slower. Why was that? Because the Church encodings do a lot of unconditional jumps. And when he represented them properly, he turned those into tests and conditional jumps. More instructions. They were slower. It's not the case anymore, because all the jumps that you get to dynamic addresses, they really screw with branch prediction. But back around 1990, branch prediction wasn't so important. And so this was actually the quickest way to implement data structures. If you want to try this at home, I should warn you, all the code I've shown you is runnable. But if you just type in exactly what I showed you, you'll get a complaint from the type checker. The Haskell type checker will say, there's an occurs check error. We cannot construct the infinite type t, twiddle t, arrow t, arrow t. Okay, that sounds bad, doesn't it? But don't worry, because this isn't all the information you get. The type checker will also very helpfully tell you the type it was expecting and the type that it got. And by the way, this is the first time I have ever had the chance to use a 3-point font on a slide. Now, I realize even this might look a little overwhelming, but don't worry, there's more. It also tells you the types of all the variables in scope. So the problem is that although you can run this code in Haskell, it's just a little bit too tricky for the type inference to understand it. So you have to add the red symbols, 2 symbols, and you have to tell the type checker what the type of the factorial function is. The black stuff is all stuff that the type checker could infer by itself. The red bit you have to add. So if you want to try it out, don't forget to do that. OK, so way back in 1940, Alonzo Church could write functional programs. That was great. But he couldn't actually run them. That was a bit sad, wasn't it? You couldn't run functional programs until around 1960, when John McCarthy implemented Lisp. Here's the factorial function in Lisp. And although it may look a little funny to most of us nowadays, Lisp was actually quite a powerful functional language. It even had higher order functions. So you could, for example, map list fact down the list 1, 2, 3, 4. Map list is what John McCarthy called the map function. So this will just call the factorial function for each of these arguments, and you get the list of factorial numbers, just as you would expect. So you could do a lot of fun functional programming in Lisp. And actually, Lisp was my gateway drug. I I read a book about Lisp, and I didn't have access to an implementation, so I wrote my own Lisp interpreter so that I could play with it. It was great education. So a lot of exciting stuff was going on in the early 60s, but I'm going to skip ahead a little bit to the middle of the decade and a truly landmark paper by Peter Landin. This was from 1965, a paper called The Next 700 Programming Languages. And this is really one of the classics in the whole programming languages area. I'm just going to read you an extract from the abstract. He says, today, 1,700 special programming languages are used to communicate in over 700 application areas. Well, Landin thought that was 1,699 too many. All we really need, surely, is one programming language, his programming language, ISWIM, which stands for If You See What I Mean, and 700 libraries for tackling different application areas. So, you know, quite a modern approach. Anyway, Landin described his ISWIM language, which has had a huge impact on functional languages ever since. For example, you can see here's the factorial function in ISWIM. Look, there's a where that is nowadays familiar to us in Haskell, for example. But I'm not going to talk so much about the language, but about something else that Landin really emphasized in this paper. And that was what he called laws. What is a law? Well, a law is an equivalence between two programs that tell you that they will behave exactly the same in any context. So you can always replace one side by the other. And this is an example of a law about Lisp programs. It says that if you reverse a list and then map list f over the elements, you get the same result as if you first map list f and then reverse the results that you get. Unfortunately, it's not quite true in Lisp, because Lisp has functions with side effects. And the left side performs the calls to f in a different order from the right-hand side. So if f has side effects, you could get different results. Landin thought that was bad. Laws are made to be followed. And indeed, he discusses this point in his paper quite explicitly. He says, you might be wondering, you know, well, what is the point of having a law like this? Because it gives you two different ways of doing the same thing. What's the point of that? Wouldn't it be better if they did subtly different things? Because then you'd have a choice. That would give you expressive power, surely, in making the choice between them. Landin thunders, no! Expressive power should be by design rather than by accident. Yes, Mr. Landin. It's hard to deny he has a point, isn't it? So Landin really emphasized the importance of laws, and I think ever since then, functional programmers have cared about whether their programs satisfy nice laws. Let me jump ahead to another landmark paper. Can Programming Be Liberated from the von Neumann Style by John Backus. Who knows who John Backus was? Okay, ooh, many people do, many people don't. So you've heard of, for example, Backus normal form, BNF. That was John Backus's invention. But in 1977, he got the Turing Award, and it wasn't for BNF. He got the Turing Award because Backus was the man who led the team that developed the first Fortran compiler. And the first Fortran compiler was the first compiler that could generate better code than a human could write consistently. And in those days, this was in the 50s, computers were so expensive, nobody cared about programmer productivity. They only cared about making the best use of the machine. And John Backus made it possible to get the best use from the machine with a high-level language instead of writing machine code. At that time, there were people who seriously thought assembly language removed you too far from the machine because you couldn't reuse the bit patterns of instructions as data if they happened to have the right value. So although Fortran, even at the time that I was studying, was the language everybody loved to hate, well, one shouldn't let that diminish one's appreciation of the enormous achievement that the Fortran compiler was. So John Backus got the Turing Award for that. And when you get the Turing Award, then you get to give a talk and to publish a paper. And of course, John Backus could have talked about how they had developed the Fortran compiler and all the techniques that they used. In fact, he later on wrote a paper about exactly that, which is very interesting too. But he chose to use his Turing Award lecture to say, no, we got it all wrong. We shouldn't be using imperative languages like Fortran. We should be using functional languages, his new love. I'm just going to read you a few phrases from the introduction to the paper because they're so wonderful. Conventional programming languages are growing ever more enormous, but not stronger. This was before C++ existed. He was thinking about languages like Ada. Inherent defects at the most basic level cause them to be both fat and weak. It's stirring stuff, isn't it? Their primitive, word-at-a-time style of programming, inherited from their ancestor, the von Neumann computer. So he goes on to explain that in a computer, certainly at that time, you would have a processor and a memory, and the connection between was the bus. And the programs were all expressed at the level of processing one word at a time. All the words you wanted to compute with had to go between the memory and the processor and back again over this one bus. That's what he called von Neumann bottleneck. It was clearly a very bad idea for parallel programming, for example, as indeed it has turned out to be. So Backus was very down on word-at-a-time programming. He wanted to program with larger scale structures. Let's follow Backus again. Their inability to effectively use powerful combining forms for building new programs from existing ones. What's he talking about? I'm going to show you some of his combining forms pictorially. So I'm going to draw some diagrams. Backus thought of a program as a function from its input to its output. And I'm going to draw the input on the right-hand side. It's just going to work better. So if this is a function or a program, Backus proposed combining forms for building larger programs from smaller ones, such as apply to all, which he wrote alpha. So alpha f would take a program that converted an input element to an output element and turn it into a program that would take a vector of inputs or a list of inputs and produce a vector of outputs. Nowadays, we call it map. Here's another of his combining forms. If you've got a bunch of programs, F1, F2, F3, and so on, you could make a construction of them, which he wrote like this. And this is a program that takes the input and replicates it and passes it to each of the functions, making a vector of the results. So those are just two examples, and there were many more. Their lack of useful mathematical properties for reasoning about programs. This is very bad. So let me show you one of those properties. Look at this program. So this is a composition of a construction with another function. This is G. And composition was one of Backus's combining forms. That's that black dot there. So this diagram can be described by this expression in Backus's language. But if you think about it, this will compute the same results as this program. But it doesn't matter whether we replicate the input, whether we take the output of G and replicate that, or first replicate the input, and then process it several times. And this can be written in this form. It's a construction of compositions of F1 with G, F2 with G, and so on. And so these two programs will always be equal. And that's one of Backus's laws, one of the mathematical properties he was talking about. So the paper talks a lot about these things, and then he also shows the kinds of programs he wants to write. Let's look at an example of that. This isn't one of them. This is a program for computing the product, the scalar product of two vectors, and it's written in Algol 60. Look at it. We take one element at a time from each vector, one word at a time. We multiply them together. We add one word into this variable c. It's very, very word at a time. Backus didn't like that. He wanted to write this program like this instead, where you take a program that receives a pair of vectors as input, transposes them. This is matrix transpose to get a vector of pairs, applies multiplication to all the elements of the pair. So now we get a vector of products, and then we just add them up. And insert is what Backus called, what we now call foldr. So that would just sum the results, and we get the scalar product very simply. So you can see this program is treating the whole value, the pair of vectors, as a whole. It's not word at a time. Backus would actually have written that like this. I think he had a little bit of APL envy. But that's really not so important. So this paper was enormously influential. I can't emphasize to you just how important it was that the man who gave us Fortran, the most widely used programming language at the time, said in his Turing Award address, no less, it was all a mistake. It's as though Bjarne Stroustrup were to stand here and say, you should all be using Haskell. So it inspired a whole generation of researchers to work on functional programming at that time, myself among them. If you haven't read the paper, Google Backus Turing Award today. The PDF of the paper is the first hit. And if there's one thing to remember from this talk, it's that if you've not read that paper, you should go away and do so. Or at least you should read the first half. The first half is just brilliant, a classic of the genre. The second half was some ideas for handling I/O, which haven't proved as influential in the long run. But the first half, it's gold. So, John Backus. Now I want to skip ahead another few years to this man, Peter Henderson. Remember the face? So Peter was Mary's PhD supervisor. And he was also very excited about functional programming. But he had two loves in life, functional programming and the artworks of M.C. Escher. This is one of those. This one is called Square Limit. I'm sure we've all seen them. And Peter wondered if he could combine the two. So in those days, so he wanted to be able to produce this picture. And in those days, if you wanted to do graphics, you had to draw pictures on a graph plotter. There was a piece of paper, and the plotter would pick up a pen and draw on the paper for you. It was very time-consuming. And you had to program those plotters by sending commands to tell the pen which way to move, very word at a time. Peter didn't want to do that, of course. He wanted to work with whole values, pictures, like this fish, for example. And he wanted to work with combining forms for putting pictures together, like this one. Here I'm using an overlay operator to overlay the fish with a double rotation of itself. Rotation here is by 90 degrees, so this is a 180-degree rotation. So now we've got two fish chasing each other's tails. That's nice, isn't it? And it turns out that this fish is very cunningly designed so that it can fit together with itself in more than one way. In fact, if you rotate it 45 degrees to get fish 2, then you get a smaller fish. And you can overlay the original fish, and I think this is fish 2, and this is a triple rotation of fish 2, and they all fit together. So now we've got a big fish and two smaller ones swimming beside it. Let's call that T. Here's another nice picture where I've overlaid 4 copies of the 45-degree fish, fish 2. And so we've got 4 rotations of it that fit together, and they give us 4 fish swimming in a circle. Doesn't that look like part of Square Limit? Yeah. He went on to define more functions on pictures, like quartet, that takes 4 pictures and puts them together into a square, equally spaced. And now you can take, for example, that picture T that had 3 fish in, and I've got 2 copies here. This one is rotated. If you put that together in a quartet with 2 empty pictures, then we get a picture in which we've got larger fish swimming here and smaller ones above. So we've got 2 different sizes of fish, but of course, in Square Limit, there are many different sizes of fish. But what if we call this picture side 1, and we make another quartet, where we put smaller copies of side 1 up here? Now we've got 4 different sizes of fish, getting smaller towards the edge. And of course, we can keep doing that until the fish becomes smaller than a pixel at least. So we can get infinitely many fish getting smaller towards the edge. Likewise, if we take that 4 fish swimming in a circle, then here I've made a picture where I've put 3 empty pictures together with that. You can see it looks a bit like a corner. But now if I fill in these other 3 parts with a smaller version of the original corner and 2 sides, one of them rotated, then we have a suitable corner for the picture, with fish getting smaller towards the edge. And so on and so forth. And at the end of the day, if you make a nonnet, that's 9 pictures in a square, with copies of the side and the corner and rotations of each of them, and this picture U in the middle, then this is what you get. Isn't that beautiful? Look, there's Escher's square limit. It's close, isn't it? Okay, he doesn't have black and white fish. That's an exercise for the reader. But he had great fun doing this, and Mary spent part of her PhD time implementing various versions of his functional geometry and drawing these fish on the graph plotter. She had a great time. But of course, there's more. Because Peter had to find a way to represent pictures. How might he represent pictures? What would Alonzo Church do? Yes, of course, a picture is a function. So Peter found a cunning way of representing pictures as a function from 3 vectors, A, B, and C, that would return a list of plotter commands that drew the picture within the blue rectangle defined by these 3 vectors. And choosing this representation made the operations on pictures really easy to define. So how do you overlay 2 pictures, P and Q? Well, you just draw them both in the same rectangle, and then take the union of the plotter commands. How do you put one picture beside another? Well, if we want to put P beside Q, we just have to split up the blue rectangle into 2 smaller ones. And then we draw P in a rectangle defined by A, B over 2, and C. And we draw Q in a rectangle defined by, this will be A plus B over 2 is the bottom corner, and B over 2 and C. Really simple. You can even rotate pictures in the same way. You might wonder how to do that. How do we rotate P? Well, we draw it in this rectangle instead, where the origin is now the original A plus B, the bottom is now the vector C, and the side is the vector minus B. So Peter defined his picture operations this way, and then he went on to prove a whole bunch of laws about them, like this one, for example. I've not shown you above, but this is easy to understand. If I put P above Q and rotate it, I get the same thing as if I rotate P, rotate Q, and put one beside the other. And if you take those simple definitions I showed you, giving a proof of this is very, very easy. So Peter proved many, many laws about his combinators. Why did he do that? He says in the paper, it seems there's a positive correlation between the simplicity of the rules and the quality of the algebra as a description tool. In other words, he's saying, finding definitions for these operations that satisfied good laws, that's how he knew that his design was right. So we see here important ideas in general from functional programming. Peter's programming with whole values, pictures, using combining forms like the picture operations, checking the laws they satisfy and using the algebra as a litmus test for a good design, and once again, using Church's idea of functions as representations. And those ideas come back in functional programming again and again. So functional geometry was a lot of fun. I want to now skip ahead to a paper from the 90s that is a personal favorite of mine. You might not be aware of it. It's a paper called Haskell versus Ada versus C++ versus awk versus ... an experiment in software prototyping productivity. And it's by Paul Hughes and Mark Jones. Paul Hughes was a giant of functional programming. He died a couple of years ago. And he was the person who took the initiative to the design of Haskell. But in the 90s, Haskell did exist, but it was very hard to get research money in the US for building real software with functional programming. However, Paul figured out that you could get it for software prototyping. Software prototyping was hot at that time. It's like microservices today. And there was a big DARPA grant for using a variety of languages as prototyping languages. Awk, for example. So there was a group who were trying to use each of these languages for prototyping. Anyway, early on in the project, DARPA decided they would check and see how people were getting on. So they decided to give everybody the same problem and a short time to build a prototype, and then they would evaluate them. And DARPA being DARPA, the prototype was what they call a two-dimensional geometry server. And it was a question of reading in data about the positions of various objects and their trajectories and constructing regions with funny names like slave doctrine and weapon doctrine and engageability zone. And then there would be objects in here like a hostile aircraft and a commercial aircraft. And the prototype was supposed to spit out some text that would say, you know, the commercial aircraft is at this point, it's in the engageability zone, it's in the tight zone, and the hostile craft is in the carrier-slave doctrine. I don't know if that's good or bad, but it didn't matter. So Mark Jones, who was a postdoc at the time with Paul, got the job of building the prototype. And of course, what you have to do to solve this problem, you have to find a way to represent regions in the plane. How might you represent a region? What would Alonzo Church do? Of course, as a function. So that's what Mark did. So Mark's regions were just functions from points in the plane to a Boolean. True if the point is in the region, and false if it's not. And that made it really easy to define functions that construct shapes. For example, a circle, how do you tell if a point is within a circle? You just compute how far it is from the origin, compare that to the radius. How do you compute the outside of a region? Well, you compute the inside and you negate the Boolean. How do you take the intersection of two regions? Well, you just ask, is the point in the first and in the second? It's just the conjunction of the Booleans. So it's dead easy. And then you can go on to define, for example, a ring shape, an annulus. It's the outside of one circle intersected with the inside of another. You can imagine, after a little while, Mark had solved the problem. And when the solutions were compared, these were the results. Here's a table from the paper. Here's Mark's solution. It's 85 lines of code. And that compares very well with 760 lines of Ada, or 1,100 lines of C++. So that was great. What I think is a bit of a shame is that Mark was very fond of writing type signatures, which you don't have to do in Haskell. So of those 85 lines, 29 were lines the type checker could have inferred for him. So it could have been a 56-line solution. He missed an opportunity there. Anyway, each group submitted their solution, and DARPA evaluators looked at them. And originally, they just didn't believe that this was executable code. They thought he's just written down some kind of spec. But no. Paul and Mark insisted you could run the code. So then they thought, well, this must be because Mark Jones is a genius, which is true. But nevertheless, they didn't trust it. So what they did was, without telling Paul and Mark, they picked a graduate student somewhere else. And they gave him a week to learn Haskell, and then gave him the problem. And that's why Haskell is in this list twice, with both the first and second smallest solutions. But you can see, with only a week's experience, his solution was almost twice the size of Mark's. Well, I thought this was a truly wonderful result. And you would think, well, what are DARPA going to say? You know, here's proof positive that Haskell is way better at prototyping, at least, than all of these other languages. So what was the reaction? Too cute for its own good. Higher order functions are just a trick, probably not useful in other contexts. So next time you use one, remember it's just a trick. Anyway, I love that paper. I think you can see why. There's much more goodness in the paper than I have time to tell you about, so that's another good recommendation if you fancy some fun reading. I want to go back now and discuss another very important idea, which is represented in Haskell, lazy evaluation. So lazy evaluation was an idea that was in the air. There were a number of people who had come up with variations on it around this time. But there are two papers in particular that are usually credited with the invention, and certainly with the invention of the name. One called A Lazy Evaluator in Europe by Henderson and Morris. Look, remember this guy? Mayor's supervisor. And the other in the US by Dan Friedman and David Wise. Cons should not evaluate its arguments. And they illuminated different aspects of lazy evaluation. They were both very inspiring. And for those of you who might not know what lazy evaluation is, the best way to, I can explain it like this. It means that when you pass a parameter to a function, for example, or when you put a component in a data structure, you don't evaluate it straight away. you wait until you're going to need it. It's like trying to get a teenager out of the house. Right. Put on your jacket. I will. Put on your shoes. I will. Clean your teeth. I will. We're going now. Oh, wait a minute. Lazy evaluation is just like that. So what I was really inspired by in these papers was I was fascinated by whole value programming. And with lazy evaluation, the whole value can be infinite. For example, it could be the infinite list of natural numbers, 0, 1, 2, 3, and so on, without end. It could be all of the iterations of a function. X, f of x, f twice of x, and so on. Now, of course, this doesn't mean when we program with these things that we're ever actually going to compute all the iterations of a function. You can't, you'd fall into an infinite loop. What it means is that it's the consumer of such a list who decides how many values are needed. So you can separate the code that produces values with the code that consumes them and decides how many it needs. And I thought that separation was really exciting and had lots of possibilities for structuring code better. For example, I had studied numerical methods as a student, and I wasn't very good at it. And partly the problem was that numerical algorithms always seemed to be very involved, and there were lots of moving parts, and they were hard to understand. But I realized I could write one consumer function for numerical methods to compute the limit of a sequence, because many methods compute the limit of a sequence of approximations. So I could take a sequence constructed by any means and just take the first value that is within epsilon of its predecessor. And then I could use that in many numerical algorithms. Here's a Newton-Raphson square root, for example. Next is the function that maps one approximation to the next one. So I can just iterate that, starting from any value. Let's take 1.0. And this gives me potentially infinitely many approximations to the square root. But I'm not going to evaluate them all. I'll just take the limit, which means I keep going until I find something that's sufficiently accurate. Here's another example. This computes the derivative of a function. So to compute a numerical derivative of a function, you compute its slope at a point x, between a point x and a neighboring point x plus h. And the smaller h is, the more accurate the slope will be, the more closer it is to the actual derivative. So this slope function computes that slope. And now, to compute the derivative, I can just compute a decreasing sequence of h's. I've chosen to take one and then halve it at each step. Compute slope with each of these h's, and then take the limit. And it's the same code for taking the limit and doing the convergence check in both cases, even though the approximations are constructed quite differently. I thought that was great. There's something else you can do here. So I explained how you do numerical differentiation, and there's this parameter h. The smaller h gets, the more accurate the result. Integration is the same. You can compute an integral by adding up the areas of a lot of rectangles. And again, the width of each rectangle is a parameter h. The smaller you make h, the more accurate a result you get. So here we've got two ways of constructing sequence of approximations that both depend on an h that is getting smaller. So what if, now the interesting thing about numerical methods like this is you can express the result you get in this form. The right answer a plus an error term, which is some coefficient b times a power of h. And then the larger the power of h, the more quickly the algorithm converges. So now, remember that I'm, in my sequences of approximations, I'm halving h at each step. If I take two successive approximations, I've got these two values, and I've got two unknowns, a and b. Think back, high school maths. If I know these two values and there are two unknowns, I can solve for the unknowns, right? How cool is that? That means I can take my sequence of approximations, and I can just take the first two values and solve and get a and b. I don't care about b, but a is the right answer. All I need is two approximations to get the right answer. Well, okay, that sounds like magic. It's not quite as magic as that, because this a times error term, that's itself an approximation. So what happens here is that if I take the first two elements, I'll get the right answer. But if I take the next two elements, I'll get a better right answer. And so I can take this sequence and construct a whole new sequence of right answers. They're more and more accurate right answers. But the point is that this sequence converges much faster than this one. It's a better numerical method with a higher order error term. And I can write a function that does that. And once I've got a function that does it, I can use it more than once. Look, here's a really fast derivative. We start off by just constructing my original approximations as before. And there's a first order error term. Let's get rid of that. A second order error term. We'll get rid of that too. And then take the limit. If I want an even faster one, I could just improve the sequence again. When I was a student, I studied by hard work doing manipulations by hand to figure out these kind of faster algorithms. And actually, all you have to do is call a function. So this works even better for integration. I really loved it because everything in it is now programmed separately. Everything's easy to understand. The approximations are easy to understand. The improvement is easy to understand. The convergence check is easy to understand. You just put them together, and you get wonderful code. This was one of the important examples in my paper, Why Functional Programming Matters. So I really loved this idea of separating the producer and the consumer, where the consumer would demand values, and that would drive the producer to produce them. And you've seen the idea of using a convergence test and numerical approximations to express numerical algorithms very, very simply. The paper also talks about a different application where the producer is constructing a search space and the consumer is the search strategy. And in the paper, I take a games program where the search strategy is the alpha-beta heuristic, which is quite a good search strategy for game trees. And because I only had a very small computer, the game was noughts and crosses. Sorry. Could do something more exciting nowadays. But I was able to build a game program that would play noughts and crosses optimally. But I didn't need to mix up the search strategy with the code that built the search space. They were both separated cleanly. And I like that very much. I'm not going to show you that in detail. I'm going to quickly mention a later paper I wrote, the design of a pretty printing library, which uses the same idea. So here, the producer constructs many ways to lay out a document, and the consumer selects the best layout for doing pretty printing. What is pretty printing? Well, if you are pretty printing source code, for example, you will often need to choose between laying out a conditional expression like this, horizontally, if it fits, or if it doesn't, laying the same thing out vertically. And pretty printers can be used for giving source code a standard format or printing data structures. So compilers have many different data structures, different languages internally, and you want pretty printers for all of them. It's a very common programming task. If you've written a pretty printer from scratch yourselves, you will know just how hard it is to get those suckers right. It's very easy to end up with very bad layout as a result. So what do we need to do? Well, we need to choose between horizontal and vertical layouts. And often in the vertical layouts, we need to insert some indentation. But of course, we don't want that indentation to appear in the horizontal layout. That would be stupid. So I defined a collection of combining forms for building a space of possible layouts. Here's how that example I showed you would look. It's built by calling sep, that chooses between horizontal and vertical layouts of the elements of a list. Text just converts a string to one of these documents. Nest inserts indentation, but only in a vertical context. So this piece of code can generate either of those forms that you saw on the previous slide. And I'd found 5 or 6 combining forms for putting these things together. How did I know I had the design right? I looked at the laws. For example, indentation is not supposed to appear horizontally, right? This is horizontal composition. So A beside nest KB is the same as A beside B, or it should be the same. But if it's A that's nested, of course, that's not in a horizontal context. It depends on the context of the whole thing. So putting a nested A beside B should be the same as nesting A beside B, and so on. And I used these laws both to guide the design of the combinators and also in the implementation. When you run my library, what it's doing internally is applying all of these laws to transform the document you start off with into the layout that you want to print. And then you need to choose the best layout as well. And I had a little heuristic that, first of all, tries to choose a layout that stays within the paper width. But it turns out that if your entire code fits on one line and 80 characters, that's usually not the prettiest layout. And so I also used a heuristic that tried to limit the width of each line of text as well. So I had a lot of fun designing this library. It's another of my most read papers. And I know it's a good idea because so many other people have improved on it since then. And in fact, if you look in the libraries that come with most functional programming languages today, you'll find a pretty printing library that if you trace back, you can trace back to my paper. It started off a whole little sub-literature on functional pretty printing. So I want to briefly mention probably what I'm best known for nowadays, and that is QuickCheck, which I did together with Koen Claessen 2000. If you haven't seen it, what does it do? It lets you write properties of your code. This is from the Erlang version. And there are combining forms for constructing properties. So this property of the reverse function says, for all x's that are lists of integers, if you reverse x's twice, you get the list you started off with. And you give that to QuickCheck. It generates 100, by default, random tests and says everything was OK. So the property seems to be true. More interesting is when the property is not true. For example, here's a wrong property that says that the list reverse is the identity function. Well, of course, it isn't. And if you give this to QuickCheck, it'll find a counterexample. Here's a list that's not its own reversal. But as you can see, this is far from the simplest failing case. You wouldn't want to debug a program given failing cases that look like this. So the next thing it does is start shrinking that, looking systematically for a smaller example. And it turns out that the smallest list that isn't its own reversal is the list containing 0 and 1. Why is that smallest? Well, if you take the 1 away, 0 is its own reversal. If you take the 0 away, 1 is its own reversal. And if you replace that 1 by a 0, 0, 0 is its own reversal. So 0, 1 is the smallest. What I want to emphasize about QuickCheck here is that it's doing the same thing. The combining forms for properties describe a space of all possible tests, and QuickCheck uses a search strategy to find a test that fails. The only difference is that here we're first of all using a random search, and once we find a counterexample, a systematic one to find the simplest failing case. But it's the same idea. Look, I only have one idea. Luckily, it's a good one. So now, just to, for the last part of the talk, I want to move to hardware. Has anybody seen this book? Oh, two people. This is 3 people. This is Mead and Conway, Introduction to VLSI Systems. And when it came out in 1979, it revolutionized VLSI design. It changed VLSI design from being about where to put rectangles on silicon to how to design the algorithms that hardware would run. Mary read this book, and she was very inspired by it. And she thought, wouldn't it be great to have a programming language that let us describe circuits in this way? And she realized that Backus's FP was already quite a good programming language. When I showed it to you, I drew pictures that looked rather like circuits. But what was missing was the notion of clock cycles, and thus of latches, clock cycle delays. So Mary added a clock cycle delay, which I'll draw as a blue box, to FP to design a language of her own, MuFP. And that inherited many of the laws and many of the combining forms from Backus's work. And it was good for reasoning about alternative designs, because you could use the laws to restructure a circuit. Here's an example law. Here's a little orange component. Here it's getting one input from the right and one from above. And as you can see, its output is delayed 1 clock cycle. But that's going to produce the same behavior if we don't delay the output, but delay the 2 inputs instead. Right, so this law is called retiming. I think it's clear that these 2 circuits will behave equivalently. OK, who cares? Look at this circuit. This is a regular array circuit. And it's a bad design. Why? Because there is a single combinational path from this input through all the orange boxes to the output. And that means that in one clock cycle, data has to flow all the way from here to here through a lot of hardware. And that, in turn, means that this circuit will have to be clocked slowly. But you can improve it. Suppose we throw in a block of delay elements. OK, so far this is not an improvement. So far we've taken a slow circuit and we've made it even slower because you now have to wait 4 clock cycles before it even starts producing output. But let's try some retiming. Look at this box. Its 2 inputs are delayed. What do we know? We know that we can move that delay to the output. Now this box has 2 delayed inputs. We can do it again, and again, and again. OK, now I'm going to keep this column unchanged, but I'm going to do the same thing to the remaining 3 boxes. And again. And again. And what I have now, because I've applied retiming, is a circuit that is guaranteed to be equivalent to the one I showed you before. You still have to wait 4 clock cycles before any output comes out. But on the other hand, now, in 1 clock cycle, data only has to propagate from here to here. And that means you're going to be able to clock this circuit 4 times as fast. So it's a huge improvement. It's an example of a systolic array. And MuFP was very good at designing these things. It even got some users. Plessy, a group at Plessy began to use it to design a video motion estimation chip. That's part of MPEG compression. And they wrote a paper about it. They said, using MuFP, the array processing element was described in just 1 line of code, and the complete array required 4 lines of description. MuFP enabled the effects of adding or moving data latches within the array to be assessed quickly. So that was great. Users for functional hardware description. What happened next was that Plessy were bought by Siemens and GEC, and they weren't at all interested in this stuff. They probably thought it was too cute for its own good. And so that was the end of that, temporarily. But Mary continued working on it, and her research student, Satnam Singh, took this work further. Satnam realized that it would make sense to combine MuFP and functional geometry. Why? Well, MuFP was very good at defining the semantics of circuits. Functional geometry could define placement. And so Satnam designed a language called Lava that used both to generate hardware layouts where you could control placement. And then after his PhD, he went to Xilinx, where he used Lava to generate layouts for their FPGAs. What difference does it make to control placement? Well, here's an example of a regular circuit, 4 adder trees, laid out by the Xilinx tools. As you can see, it's a dog's breakfast. Here's what you got from Lava, where the structure is regular and clearly visible. And the difference that makes is, A, this will perform better, but more importantly, because it's laid out efficiently, it'll fit on the chip. And for many problems, there were many Xilinx customers who had problems that were just too big to fit. And Satnam was able to fit them by reprogramming them in Lava. So he had Lava as a Haskell library, and he would just generate Windows binaries and give them to Xilinx customers. He wouldn't tell them what was in them. He said, here's a generator for your problem, and just don't ask. So this was quite successful in practice. I want to talk about another famous hardware incident. Do you remember this? Yes, so here we're taking a number starting with 4, dividing it by a number starting with 3, multiplying by the number starting with 3 again, so we should get back this one, and subtracting it from the same number. Of course, we should get 0. On flawed Pentiums, you got 256. And Intel, in the end, they had to replace very many of those Pentiums. It cost $475 million, which was a lot of money, even for Intel. Of course, they had a lot of duff Pentiums after that. So what did they do with them? They put them in key rings, and they gave them to their employees. I've actually seen one of these. And on the back it says, bad companies are destroyed by crises. Good companies survive them. Great companies are improved by them. What was the improvement? They hired this man, Carl Seeger, a former student at our university who'd learned lazy functional programming at the time, didn't understand what it was for. But at Intel, he built his own lazy functional language, which had hundreds of users within the company. And they used that for designing hardware, for writing the specifications, for scripting their tools. They built theorem provers for proving that circuits were doing the same thing before and after transformation. And this was a huge success. This is one of Carl Seeger's own slides. And you can see that everything from the microarchitecture at the RTL level down to the actual layout was done using this lazy functional language. So why hasn't there been another Pentium bug? It's at least partly thanks to functional programming. Many people don't know that. They had a lazy functional language. Here's something else they did. They built cert spaces, representing, for example, ways to lay out certain kinds of circuit, and selection criteria that could pick the lowest power implementation. So again, we see the same ideas coming back again and again. I want to show you one more thing because it's really cool. BlueSpec, have you heard of that? It's functional programming for hardware. It's the product of Arvind at MIT and one of his students. And what it gives you is a Haskell-like language for the architecture of your circuit, together with some very clever atomic transition rules for doing the actual hardware modeling, from which the compiler can extract lots and lots of parallelism. So it's a very high-level language for expressing hardware. And just like functional programming in other contexts, that lets designers explore better algorithms, make architectural changes easily, and get very good performance as a result. There's a very nice paper about this by Nikhil, which there's a reference to there. So this lets you basically take Haskell programs and put them on hardware. Which Haskell program would you like to put on hardware if you could? Guess which Haskell program I would like to put on hardware if I could. QuickCheck, of course. And that's been done. It's called BlueCheck. It's done by Matthew Naylor and more in Cambridge. So they've got a version of QuickCheck in BlueSpec. You can synthesize it and put it on an FPGA, and then it generates and shrinks tests on the FPGA. And FPGA designers, they're blown away by this. They've never seen anything like it. So it's becoming a big success. I think that's just great fun. Okay, so we've come on a long journey today from church numerals all the way down to QuickCheck on an FPGA. But throughout the whole talk, we've seen the same ideas coming back again and again. The importance of programming with whole values, not word at a time. Combining forms for putting things together that satisfies simple laws to tell us when our design is good. And making use where we can of functions as representations. I think we would have made Bacchus proud. Thank you.